So this is Laboratory 8 Hints. So in Laboratory 8, we're going to go through how we use parallax to estimate the distance to a nearby star. There's going to be lots of steps. If you look at this is a 10-page document. Some of them, like this first page, is looking at some figures, drawing an X on which star you think is moving. Pretty simple. But I just kind of step by step, we're going to go through how we estimate distance to a nearby star. So after going through that first easy part of just looking at the figures, we have this chart here that I want you to print out, fold. You're going to need to punch a couple holes at point X and Y, which is just going to correspond to different places the Earth is around the Sun. And you'll set this on some cardboard and you'll stick some pins in here like you see in the figure. And as we look through the one figure, we can draw a line from Y here to the background stars and see what's going to happen. As we look at the figure, we see that maybe star N is going to line up around C. And when you look through it, it might be slightly different than when I'm drawing this on the paper. But as I look in the other hole, we see with the blue line that the star is going to appear to move just because of looking at the star on these stationary background images as they move. Go ahead, cut the holes, look through it, and see exactly how parallax works. Now as you answer these questions, sometimes in the lab write-up it doesn't have a lot of room. Yeah, you can try to write what you want in these spaces here as you try to answer these questions, or if you want to just type these up on a separate sheet of paper and include that in what you hand in later, that would be fine too. Now in part 2 of this, we're going to be looking at some actual pictures taken from some observatories and try to figure out exactly how this works in real life. So, this next couple of sheets are kind of explaining exactly what's going on. And here we're looking at what the similar triangles are looking at. So as I look through the telescope, and I look at the different angles, I have these similar triangles, and it asks you to sketch these out. But if I drew a line right in the middle here, this triangle, this right triangle, and this right triangle are going to be similar. So we'll be able to use just the ratios of the different sizes to understand what's going on. In this case, we're going to use this large triangle from X and Y. That's going to be the diameter of the Earth's orbit and how our view changes. And this is going to be the length of the telescope. So we're going to fill in some blanks. I'll show you a very simple equation. I'll show you exactly how to use it. So as we read through and see how this all works, we fill in answer all the questions. We get to this formula for calculating the distance to a star. Now, it's a pretty simple formula. It's all it is comparing two ratios. And what we're really wanting is this distance to the star. So to solve this, we're going to multiply both sides of the equation by the diameter of the Earth's orbit. So then we get the simple equation that the distance to the star, which is what we want, is going to be equal to the diameter of the Earth's orbit, that's this line right here, times the focal length of the telescope, that's this line right here, the whole thing divided by the parallax shift. So this is going to be our equation. We're going to take this number, the diameter of the Earth's orbit, multiply it by the focal length of the telescope, and divide it by the parallax shift. And in the following figure, I'll show you exactly how to calculate these. So as you read through here, it explains what's going on, but essentially Barnard's star is moving in this direction just due to its orbital motion around the galaxy. The parallax we're looking at is the shift that's going back and forth this way. And so if you look very carefully right here, you see these 3 points of light. Those are different pictures of Barnard's star taken over 1.5 years. So what we're going to do is we're going to draw some lines in on here, and it's pretty small. So you're going to have to use a real fine tip pencil or pen in order to really do this. But what we're going to be doing is we're going to draw in on the figure here a line that goes from A1 to A2. Draw it as straight as possible. You use a ruler. It's hard to use a ruler on my iPad when I'm doing all these figures. And then we need to draw a perpendicular line that goes through B. The parallax motion is going to be this distance between the red line and B. So that's the distance that we're going to measure, and it's going to be pretty small. Do your best to, if you've got tick marks on your ruler, right, millimeter tick marks, and you can line up one here, and the other point is right here. We can kind of estimate that. It's going to, if this was it would be 1 point, maybe 1.8. Do your best to estimate how far it is. It's going to be a rough measurement. We would have better instruments if we were doing this in lab, but I want you to just kind of get a feel for what they do in a lab to figure out parallax shift. So now in Q12, you need to write the telescope's focal length in millimeters. They give it to you, it's 10 meters. So we need to figure out how many millimeters that is. It's just 10 times 1,000 millimeters in a meter, so it's going to be 10,000. We also are given the distance xy, or the diameter of the Earth's orbit, in kilometers. So I just want you to write those two down. Now, we're going to use our figure. It says step by step how to do what I just said, how to trace where the stars are, and then use on another sheet of paper, draw the lines in, figure out the line A1 to A2 and the perpendicular line to B. Measure again distance from the perpendicular line out to B. That's your parallax measurement. And then you'll measure that step right here in millimeters. And that figure has actually been enlarged 10 times in order to make it even possible for you to measure it. So you're going to take whatever value you have in Q14 and divide it by 10 and write that down here in Q15. That's your actual parallax shift. Now we can use the equation we just did to figure out the distance to Barnard's star. So if we do that, remember it was the distance was equal to the diameter of the Earth, which is what we wrote down in Q13. It's the diameter of the Earth's orbit, not the diameter of the Earth's orbit. And we multiply that by the focal length of the lens, which is what we wrote down in Q12. And we divide that whole thing by the parallax shift, which is what we just wrote down in Q15. So Q13 divided by times Q12 divided by Q15, and that will give you the distance in kilometers to Barnard's star. Now, as we learned in the lectures in the book, there's more convenient units of measurement than a kilometer. Q17 is just wanting you to figure out how many kilometers there are in a light year. I'll go through that calculation really quickly with you. The speed of light, we said, is 300,000 kilometers per second. So we say 300,000 kilometers in a second. And we know that, remember, converting is multiplying by appropriate units of one. So we know there's 60 seconds in 1 minute. We know there's 60 minutes in 1 hour. We know there are 24 hours in 1 day. And there's 365 days in a year. So we multiply that out, and we know that the speed of light is 9. Sorry, that 9 didn't turn out well. 9.46 times 10 to the 12th kilometers in a year. Algebraically, we see all the units again go away, the seconds go away, the minutes cancel, the hours cancel, the days cancel, and I get kilometers per year. So if I want to know how far a light year is, how far does light go in a year, we multiply that by 1 year and we get 9.46 times 10 to the 12th kilometers. You can multiply that all out. You can just copy down what I have. You could also just Google convert 1 light year to kilometer and it will convert it all for you. Now, we want to use this conversion factor to figure out how many light years away Barnard's star is. So, whatever you got, say, X kilometers. I don't know how many kilometers you get. We're just going to multiply it by 1 light year divided by, then, 9.47 times 10 to the 12th. And you're going to get your answer. I can't work that out because I don't know what you're going to get from your measurement, but it's fairly easy in your calculator to just divide whatever you get in kilometers by 9.47 times 10 to the 12th. Question 19, the last question, is say, all right, here's another one, another star, Alpha Centauri. The parallax shift is 0.073 millimeters. Calculate the distance of this star from the Sun using the same calculation that we did above. When you're all done, scan it, turn this into Angel as a PDF. If you've written down all your answers in a Word document, print that out and scan it with everything else, and then you'll be done with Lab 8.